Thank you, and thank you for being patient with waiting for me. So I want to talk today about 3D object detection in the wild. I do not work in robotics, so do not treat me well. But I've been thinking a lot about 3D problems, and I understand how in robotics 3D problems are very important. And so I kind of wanted to give my view on the field of 3D and how we could improve it so that we could think about robots in the wild that perceive things, so that you guys that work in robotics don't have to think about perception. You can just work with managing your hardware and making the legs go the way they should go. So this is what I want to cover today. I want to talk about 3D from the perception side. And I am at core and always will be and forever a recognition person. So I care about taking images and understanding what they contain, interpreting them in various ways. And there's been a lot of great work done in this field for the last 10, 15 years. This actually 2D recognition, recognizing objects in 2D has been one of the most prominent problems in computer vision for the last decade or so. And I will argue, and maybe you'll disagree, that it is likely the biggest win computer vision has seen, solving some of these problems at a state that are used to the point where we can actually build applications. And I want to give you an anecdote for this. When I joined Meta in 2016, various teams at Facebook, including Zuckerberg, did not see the potential of object recognition in any products. They're like, what are we going to do? We don't need object recognition when it works, so it doesn't work well. I don't think we can sell more products by having a janky like purse detector. Who cares? And then Masquerade came along, and we showed that you can actually do this for a variety of categories, and so well that now has turned completely around. There's now no product, no app that works for content in the space of content understanding that's not using an object detector in the back. So this is exactly why I think it has been one of the biggest wins in this community, but it has also been one of the most boring wins. And why that's boring is because all of these methods and all of these great success stories and all these awards that some people have gotten assume that the world is a 2D grid. And obviously, I don't need to convince you, you're all robotics folks or robotics adjacent, that is really not the case. And if we want to move beyond just trying to sell purses to people and whatever other products, and we actually want to build some more exciting applications like embodied tasks, robots, self-driving vehicles, or other types of means of transportation, or even assistive technology that's something I'm very excited about, VR, AR, whatever you want to do, you need to move beyond the 2D grid. So this has been my mantra for the last few years, that, that robots act in a three-dimensional world. So 2D scene understanding is really not that useful. So, and for embodied and general tasks, we really want to get to 3D scene understanding. Now, the question is, what is 3D understanding? The problem with 3D is that it's so wide, it's so broad as a topic that it's very hard to define. And I'm making an attempt here, mostly to maybe think about it, discuss it later, into separating into two axes. The first axis is, how many views per scene do I assume I have? I could assume I have one scene per view, or I could assume that I have one view per scene, or I could assume I have 100 views per scene. And the other axis is scene complexity. Do I assume real world scenes? I think we should. Or do I assume single objects on top of a table? And it's my belief that a lot of work has been falling in various parts of this plot. We have this part to start with, where models assume that you have 100 or more views per scene, and they try to reconstruct and understand the scene, either real world or a single object. And some examples here are SFM or NERF. And I know this is a big debate on how NERF and how useful they're going to be for robotics. I actually don't think that these methods that assume 100 views per scene are useful for robotics. Okay, that went well. And the reason is that imagine a robot that goes into a new terrain, a new scene, that it enters a new scene. For it to be able to reconstruct the scene through NERF or SFM, extract the point cloud, it needs to first figure out how to go about the scene to collect these 100 views. And they're not random views. They have to be 360 covers of the views in order to reconstruct it so well so that it can now act with that reconstruction in place. That seems like a chicken and egg problem. When is it going to act? It has to act in order to capture, then it has to reconstruct from the capture in order to act. That seems bizarre. However, there are other applications in this space that where NERF and SFM are useful. Hollywood, I think, perhaps maybe VR, like gaming. These might be potential applications for these types of methods. So I kind of want to move now to the more useful side of this plot, which is assuming that you have one view per scene. And we're going to start with single object scenes, and that which is something that has been studied very much to an excruciating point. You have all these projects on doing single object 3D reconstruction. They're mostly be done with objects like ShapeNet, which are synthetic objects that you render in this white void. Again, I think a little useless. But thankfully, and maybe through and thanks to these works that were in these synthetic data sets, we now see works that operate actually more in the wild for real world single objects, but at least more complex objects. And we have this paper that we're presenting this Wednesday on 3D reconstruction from any objects like Spyro from Nintendo. You guys know? Okay, good, because I gave this image in another workshop and nobody knew what it was. And I was like, okay, maybe I'm too old, but Nintendo, if you're born in the 80s, you know what I'm talking about. But now I want to move to the more challenging case of reconstruction of real world scenes from a single image. And this is definitely a problem that is underexplored because it's very challenging. And so I kind of want to give you my ideas and some progress in this direction on 3D object detection in the wild. You take an image, any image, and you detect the objects. You predict what objects are on the scene, but you predict them in 3D space. That means that now your output lives in 3D, which means that you can actually look at it from all possible views. So you see this image right here of this urban scene. And you get the reconstructions and also the layout if you look at it from a top view. And what you see here, which is this grid, are tiles of 1 meter across 1 meter in size. So you actually get metric outputs in your reconstruction. So this is exactly what I want to cover today. 3D object detection in the wild. And when I say in the wild, I mean truly take any image from the web, an image of the scene, and be able to detect its objects and predict their 3D properties. And this is joint work with some people at Meta, including led by Garrett Brazil, and with Abhinav, Julian, Justin, and myself. So first, I kind of want to introduce the problem. So I know that maybe a lot of you are familiar with the problem of 2D object detection, where you're given an image and you want to predict for every object, detect every object in the image that you're going to describe with a category label, chair, sofa, floor mat, etc. And a 2D box that consists of its XY center in pixel space and its width and height, again in pixel space. This is a pixel space. It's a fake space. It's a comfortable space. So now 3D object detection has exactly the same definition. But instead of predicting an object in pixel space, you're now predicting a metric space. So it's center, it's now XYZ in metric space. And its dimension is width, height, and length, again in metric space. Metric space is meters. And in addition to these properties, you also have a pose of the object. This is the pose of how you're going to rotate that cuboid so that it tightly fits the object. Any questions so far? Okay, so that everyone gets that. So how are we going to go about this? So the first thing to note is go back and see how did 2D recognition win? How was 2D recognition able to make progress? And they were able to make progress by having diverse and complex data sets like Coco and Elvis. Now in 3D, these data sets unfortunately do not exist. And actually, there's something that's even weirder that's happening, is that the problem with 3D object detection is actually studied under two different lenses. The first one is the urban lens. So this is data sets that were captured by a self-driving car. So this is a kitty as an example like this, where all of the data sets are taken from the point of view of the driver. And what happens when you're studying a problem in this narrow space is that you start making assumptions that are not just generally true. For example, a lot of work in urban domain assume that all the objects lie in ground plane. Of course, that's true in the urban domain, perhaps, but here's my object, so that is my laptop on top of this stand. So it's not generally true. And then it's also the visual domain. Not all urban scenes are actually from the point of view of a driver. These are also urban scenes, not from the point of view of the driver. And if you try to apply any method that was trained on Kitty on these scenes, catastrophic failure. Then there is the other domain, which is the indoor domain with data sets like CenterGBD, which are depressing small apartments of students and offices. I've been a student, I know what it's like, but there is not this diversity of indoor space that is true in the real world. And also most objects are very close to the camera. Actually, the largest distance of objects in CenterGBD is 6 meters. 6 meters from me to maybe you. So all of you in the back is like, you don't exist. That doesn't also make sense. And of course, again, it's the visual domain of not all indoor apartments are student apartments with one desk and one chair. You have fancy lofts, you have bars, you have churches. The diversity of indoor space is vast. And then of course, there's also the intersection of, here's an image of urban domain with a bike and a couch. So you have objects from both categories that none of the existing methods were actually able to tackle. So I'm making all of this introduction to say that there hasn't been a comprehensive approach to solution to the problem of 3D object detection that would be able to tackle all of these domains at once without making assumptions about the nature of the objects and the scenes. And this is again exactly what I want to cover today. I want to cover this method that we developed that is able to tackle all of these things for over 90 object types of all scenes. And of course, the first thing we had to do is figure out our data set. So what data are we going to use for this problem? As I said, data sets in 3D are not as popular or not as big, not as widely developed as in 2D. But luckily, since 2019, there were all these wonderful data sets that were released, not for the problem of 3D object detection. They were released for a variety of other problems like inverse rendering, point cloud reconstruction, and so forth, that could actually be repurposed for the problem of 3D object detection. This is exactly the opportunity that we saw and we took, is to take all of these data sets collected from a variety of people in the world and combine them into one data set that is diverse, that combines all of the domains and has 3D annotations that we had to repurpose to make useful for this task. And so this is how Omni3D came about, which is a collection or a concatenation of all of these data sets. There was a lot of work behind it. And the result was a data set of over 3 million object instances, 230,000 images across domains. And here are a few statistics on the Omni3D data set. So here you see the categories and the frequency. So we have our long tails, as we always do. And of course, there's some objects that are more frequent than others. For example, person, chair, I think is very frequent, and other ones that are not, like bathtub, I think is not very frequent. So there's the distribution, but the most interesting one is the depth range, and this because it's also the most challenging aspect of this problem. And here we plot the distribution of depth and the density of the objects, where you see where this plot goes all the way to 50. However, our biggest depth, like the furthest away the objects are in this data set are 200 meters, which our model has to predict. There's a vast difference to CenterGBD that was only going to 6 meters in depth. So we have a lot more analysis in the paper that I want to go through for sake of time, but we try to summarize the data set and actually show how it is a very comprehensive, all-inclusive data set for this task. And then the next step, now that we have a data set, is train this model that will be able to tackle this problem without making any assumptions about the domain, have no priors about objects and distributions and depth, etc. And this is how we came up with our QBAR-CNN method, which is what we consider a baseline for this data set. So the QBAR-CNN is a very simple model that outperforms all other models, not only on Omni3D, but also in the single data set benchmarks, and has what we think are some of the most generalized abilities to generalize to new domains. So we actually applied QBAR-CNN to images from Coco, and we see that it actually works, which is actually the first time that we saw that happen. If you take other models that were trained on these single images like Kitty and ThoroGPD, they actually completely failed to generalize. Of course, there's still a lot of limitations. I'm not trying to argue that the problem is solved, and you'll see from the numbers that performance is far from solved. But I want to make the point of training on large data sets will get you more towards generalization than training on single domains. So what is QBAR-CNN? Well, we tried to make it very simple, almost to the point where we were sure that reviewers will nag about what is the novelty here, because we wanted to remove all of the extra bells and whistles that we saw were being published in the past few years on 3D object detection, and make something that's easy to build upon, modular, that you can extend for your problem. So it contains findings from both state-of-the-art in 2D and 3D object detection, like here, and I want to cover maybe a few of them in the remaining minute that I have. So QBAR-CNN builds upon faster RCNN. This is this family of object detectors that takes an input image, embeds it into a backbone feature map through a network. It can be a CNN, it can be a transformer, whatever people come up with. The backbone is really not, is a plug and play. It's really not attached to the design of the model. Then after the feature map, this is where your task-specific heads start. So you attach an RPM, which is a region proposal network that detects where are plausible objects in the image. This is done in 2D, and we had to deviate a little bit from the original design of RPN and faster CNN. Originally, RPN was designed to do objectness. We deviated, and we are predicting IOU-ness. So we're predicting the IOU value with the closest ground truth, which is very critical when you have data sets that are not exhaustively annotated. And Coco and Elvis are exhaustively annotated, or the information of exhaustive annotation is there, but Omni3D is by design not exhaustively annotated. So ObjectNet will penalize what actually be detrimental for this, while IOU-ness bypasses this. Again, if you want to know more about this, go to the paper where we have an extensive discussion. And the next step is our 2D head, which predicts the object in 2D. And of course, the novelty here in the design is the cube head, which predicts the 3D properties of the object. These 3D properties combined are making up the 3D center, the 3D dimensions, and the pose of the object that leads to this cuboid predicted in 3D space that is then compared to the ground truth, and this is how we train the model.
Sure, did they take questions during the talk?
Yeah, absolutely.
Can I ask?
Yeah.
I didn't understand the IOU-ness is for like as a loss, like if there is no bounding box at a certain location, you cannot. So how does that actually help the inexhaustive annotation?
Yeah. So if the ground truth is missing, so in objectness, you're making a very hard decision about whether the object is there or not. In IOU-ness, you regress to an IOU. So it penalizes models less by having missing ground truths.
I see. So
And this is actually a common trick used for open vocabulary detection.
I guess there's use a particular kernel or something to make it not penalize us.
You don't make it a kernel, but you are fixing so you are assuming that you're above a threshold. You're going to regress above a threshold, so it learns to understand objects rather than classifying 0 or 1, which is a much stricter decision to make. Okay, so I quickly want to cover how we set up the objective here, and I'm going into the nitty-gritty details. So if you snooze off here, I think it's totally fine, but I find this interesting. If there are students in the room, I think that you might learn a few things. So for 3D object detection, now that we are predicting more properties about objects beyond 2D. Actually, we're predicting 4 sets of parameters. We're predicting UV, which is the projected 3D center in 2D. And we're also predicting the depth of the object. These two parameter sets make the 3D center of the object via on projection. We assume we know the focal length of the image. Then we'll predict the width, height, and length of the object. Again, this is 3D dimensions in metric space, and we use a log space, and we predict the pose of the object. So we predict all of these 4 sets of parameters. Now, if you were asked to set up a model to train this, what would you do? You would define a loss that looks like this. 4 different losses on all of these 4 different sets of parameters, and some weights in front of these losses to weight them because they're all kind of different. So you need to figure out how to put them together in the objective. There is a big problem with this. First of all, it's ugly. You have all of these 4 losses. But basically what it means is that now we're faced with this problem of hyperparameter tuning of all of these weights. We also have specialized losses, and that actually becomes a problem. What is the best loss to predict depth? That's actually an open question. It can be predicting 1 over Z, it can be bending. It's not clear what is the right loss for depth prediction. Also, what is the right loss for poses? Again, an open question, and actually depends on tasks. So not only do we have to do parameter tuning for the weights, now we're also faced with different variants of losses. And so now the grid search space becomes large. Now we're wasting a lot of GPUs, which feels really bad. Like we have PhDs, we should be smarter than that, right? So we didn't do this. This is not the loss that we defined. We actually did something different, which is cute and a smart idea that we call entanglement. And then we did this entanglement. But let me go first to describe entanglement. So we have these 4 parameter sets that we're predicting. And I told you that if you combine these 4 parameter sets, you can actually get to a bounding box. You have the center, you have the width and the height, and you can actually convert these parameters to a point cloud where the points are the vertices of a 3D box, of a box in 3D space, 8 points. And this function E3D that corresponds to this box is actually differentiable. It's important. So now I have a way to convert these parameters that I don't know what to do with them in my loss function to a point cloud that describes the 3D bounding box. And now, of course, I also have the ground for 3D bounding box, which is also another point cloud. And so what I'm going to do is I'm going to compare these predictions, not by going to the parameter space, but by actually predicting point cloud. So I'm going to take a point cloud distance like a chamfer distance. So you've seen now that I've moved away from having a loss on all of these different parameters to having one loss that combines all of them with a very nice and elegant point cloud distance. However, there is an issue here. I don't know if you've seen it, but if I have a wrong prediction, and I'm going to have a lot of those during training, it's very unclear which set of parameters is a culprit. Who is to blame for my wrong prediction? And this is a problem because I've entangled my losses. So what I'm going to do is I'm going to actually now do, based on this loss, I'm going to go into disentanglement, where I'm going to define more losses, but where I'm going to replace all of these parameters, apart from one set, with the ground truth values. So this is the disentangled version of this loss. And I'm going to do this for all of my parameter sets, resulting in a loss like this. So I'm going to have my disentangled loss for all my variables. I'm going to have my tangled loss. And now you're going to tell me, Georgia, what are you talking about? Have you lost your mind? But you're back to summing a bunch of losses together. Yes, but all of my 3 losses are not homogeneous. They're chamfer distances. There's no need for weighing because of their homogeneous. And also, we're no longer arguing with co-authors about what the right loss is for various variables. And that's important because it brings peace to the group. Okay. And I'm going to show you how actually this is better than grid search, and I'm going to show you a little later. So that was loss defining the loss. I'm not done, nowhere near, but I have more minutes, so you're going to have to bear with me. So this is how we define the 3D loss. Now, I actually want to put all of my losses together. And remember, my network is predicting 3D objects, but it's also predicting 2D objects, right? I'm doing 2D object detection and I'm doing 3D object detection. So I actually have a loss that's 3D. I described what that was before, and I now have a 2D loss. And again, students, you'll know what I mean, but when you have these two losses, you're not going to something like this, right? They're completely different, 2D and 3D different tasks. So you need to weigh them differently. And actually, you're going to say, well, the 3D task is harder than the 2D task. So I'm going to put a weight in front of the 3D loss. And maybe that weight should be something that's smaller because the 3D task is harder. Again, this is an arbitrary decision, and we want to move away from arbitrary decisions. And instead, we actually want to give the model the freedom to decide how to weigh its different losses. There might be cases where the model should not weigh its 3D detections very much because they're very occluded and it's a very hard problem for the specific image. But there are other instances where 3D detection is easier sometimes than 2D detection. So we don't want to penalize, or we don't want to set a weight to the model so that it ignores various aspects of this problem. So what we're going to do instead is actually something that is probably my favorite feature of this model, is defining it as an uncertainty specific quantification problem. So we are going to put a weight on top of the 3D loss, which is going to come through this new value that is output predicted for every instance by the model. So this mu measures the model's 3D uncertainty for each prediction. And let's look at this loss and what it does. So if mu is large, which means that the model thinks it's uncertain about its 3D prediction, then the 3D loss is downweighted because x to the minus u is a small value, but you want to penalize the model for not being certain. So you're going to make it an added, you're going to add it. You're going to add the uncertainty to the loss. If mu is small, that means that the model is certain for its 3D prediction. The weight on the 3D loss is high, and the additive term is small, so no linear penalization. We don't have supervision for mu. The model estimates it based on the appearance cues and how the objects look in the image because it's predicted from the image for every instance. So it's kind of like a self-learn type, though I hate these terms, but it's important. There's no supervision. The model has to predict it. The model has to self-calibrate in terms of 2D and 3D. Okay. Great. So this covers how we set up our training objective. Now you're going to say, okay, finally, we have a training, we have the model, we have the data, so we're ready to train. Yes, we're not. There's another challenge that we need to overcome, which is maybe my second favorite aspect of this paper and the contribution, which is understanding some of the challenges and the sources of variation in recognition for 3D. So, now that I'm a faculty at Caltech, I have to teach all these students how to do object detection. And one slide that I show them is all of the sources of variation a model needs to overcome when it has to solve for 2D recognition. I stole this slide from Ross, but it really nice encapsulates what are all the problems, all of the source of variation that a model like MaskRCNN or FastRCNN has to overcome to nicely detect objects. For 3D, you have all of these, and now you have an extra one that was not relevant before, that was not relevant for 2D. And it's simply the following observation. So Omni 3D images were captured by a variety of sensors. Remember, we take images from a variety of groups around the world that use any type of sensors. We don't have any control about the sensors that they used, which means that now our data and our models will generalize across sensors. That's great. We don't want to overfit to a sensor. That's absurd. That's not useful. But it inserts ambiguity. And this ambiguity was actually explained by Euclid, probably paraphrasing Euclid, who said that an image can actually be explained by an infinite combination of focal lengths and object depths. How many of you agree with that? And why is that? Why is that the case? Small x equals f capital X divided by z. Camera model, projective, pinhole camera. That rule means that there is always an infinite set of possible depths and focal lengths that explain the same image. Yes? I'm paraphrasing Euclid. Okay, great. Okay, so this means now that, remember, my model needs to predict depth. And even though I know the focal length, the space of prediction that I have is actually has many modes because of this ambiguity, which means that making a network predict in the space that has many modes is the worst thing you can do. Neural networks are great at detecting modes, are predicting modes. They're not, are seeking modes. They're not good at doing other things. So you want to create a space for the model that is unimodal, that has a one mode, so that it is able to perform well. So what we do with this in mind, we actually do not operate in this world space of these ambiguous Z's that can be anything. And we operate in this virtual camera space, which assumes that all of the images in our data set are taken by one sensor of a specific image height and a specific focal length. And it turns out, thanks to trigonometry and thanks to Euclid, that there's a way, very simple way in which you can actually convert the world space into the virtual space. And now this virtual space is actually much more friendly for neural networks to predict and to predict depth.
We have the workshop paper presentations.
Yeah, so there's more detail and more discussion in the paper, but I want to kind of tell you a little bit about the benefits of virtual cameras, because there is an added benefit that we're not discussing right now. So the first benefit is that now I can train my Cuber CNN on all of these images that were captured by all of these many sensors, which is something that I have in Omni3D. And now you're going to tell me, okay, Georgia, but like 3D object detection has been happening for many years. Why are you the first person to have to deal with this ambiguity and have to resolve it? Well, the problem is that all the previous 3D methods that were doing 3D object detection were working on a single data set captured with a single domain. And when that is the case, you don't have this ambiguity. You can just, you overfit to the sensor. But when you're trying to train this model in Omni3D, which is this concatenation of all of these data sets, now you're all of a sudden faced with this problem. And then there's another added benefit. Now I can finally train my object detector in 3D with data augmentations. I'm sure a lot of you train object detectors. You know that data augmentation, scaling images, is the most impactful way of getting to robust and good performance. You take your image, you scale it, and then you crop it perhaps, and you go on with your setup. Scaling images, so data augmentations, have the same exact effect as sensor ambiguity. And prior methods were actually shying away from using data augmentations when they trained these detectors. Yes, previous methods of 3D object detection were not using data augmentations. That sounds bizarre, but that was the case. And so what we're doing right now with this virtual camera is actually allowing us to train our object detectors, bringing back the powerful, though hacky, I agree, but very powerful data augmentation schemes, which are so useful for training good object detection systems.
Thank you for your okay, so
Someone's unmuted, yeah.
I would like to start with the question answering as just a general kind of introduction. BQA is an inherently multimodal task where
Hi,
we
can we
have an image and corresponding text,
yes.
and the system
Maybe I can find them. Hold on.
answer the
I can control
question. So in this case, you have an image of a
the
person
mute
with
them,
a
but
banana mustache, and the question, what is the mustache made out of?
okay.
Okay, great. Okay, and then, okay, great. A lot of people are multitasking apparently. Okay, I know I've covered a lot of things, and that is the one lesson of a lecture. Don't try to jam a lot of things into one lecture. But the final thing I wanted to say is just about how to model object rotation. And we have a very nice discussion of why we actually picked allocentric versus egocentric. And I'm going to just sort of skip that. But if you want to know about why we made this choice, please go to the paper and read more. And maybe I want to convince you that all of these things that I try to discuss or presented today actually do have impact on performance. So the first ablation is the impact of virtual cameras. And here I'm showing you our model Cuber CNN trained in its final version. This is the yellow bar. In the first bar is without virtual depth, without virtual cameras. And the second bar is a model trained with augmentations but they're not controlled with virtual cameras. And you see how both of these versions actually suffer because of the lack of virtual cameras. And when you add that feature in, you're actually seeing a very healthy gain in performance. Another thing is that virtual cameras are actually not a feature that's specific to CubeRCNN. There can actually be a feature that is applied to all models. And we did exactly that. And we saw how various methods are actually gaining in performance by having this feature enabled. And finally, all of the other designs that we have, like the 3D uncertainty with disentanglement, which all lead to healthy gains. So the 3D uncertainty, without 3D uncertainty, there's a big gap in performance. So 3D uncertainty is actually good. And without disentanglement means that we actually did search over the possible loss that we have. So we expected things to be the same, but with using much more compute. And the final version, where we don't actually have to have all of these discussions and ambiguities about what losses to use and how to tune them, actually does even a little bit better than grid search, which is fantastic. And finally, I know I need to show some images. So here's some detections, some outputs, some predictions on images for scenes from a single image. So what you see here is the input image. In the second column, you see the detection superimposed, and also a top view of the detections, where again, this is a 1 meter cross 1 meter tile, just for you to understand the scale of the scene. A few more. Some urban scenes to keep the urban people happy. And here are also some results from COCO images. We don't know the focal length, but we set it to a value which is like a common value that modern sensors use for images. Some other images, and perhaps one of the most exciting results that we actually took CubeRCNN and we applied it at a frame-by-frame basis to a capture from this AR headset from Project Aria. It's like these glasses that are kind of nerdy looking, but they're nice. They have all of these cameras, so you can actually capture as you walk through scenes, and they actually have poses with it. So what we can do now is that actually we can track objects, detect and track objects at the same time. Okay, and I know that I'm a little bit over time, and of course, all methods have limitations. Actually, this is a very unsolved problem. You saw performance was at 24% IP. That's very low, so huge room for improvement. And now that you have a data set, you have a baseline, this is a great problem to start working on. So the limitations here are definitely when you have object configurations and layouts that are out of domain, like this case right here, where the model really doesn't really know what to do. Doesn't want to predict the two cars, a truck and a car actually within each other. It has never seen that before, so it's really struggling with that. And other similar cases where you have some sort of out of distribution layouts in the scene. Oof. I'm done. Thank you.
If you have any questions, you can just come to the, yeah.
Thanks, Professor Georgia. Thanks for the great talk. I'm a Chinese student. I have a question for you. So I have said that we assume a virtual camera, right? So we can avoid a lot of inconsistent ground truths I assume the constant focal length, but we also assume that we have the camera that look front, not look from any angles, but our image is not that ideal, right? So
where is your camera? Where is your image not ideal? I didn't get that.
But I think we assume that model is kind of we assume that the virtual camera has a constant focal length and it's may look front, right?
Yeah, so nothing changes in the camera. The only thing that changes that we kind of play around a little bit with the height and the focal length.
Yeah.
But nothing changes in the visual domain.
I see. But
here's the space. Now you're operating at a space. But by doing this normalization in this virtual camera space, you're operating this virtual depth space, which is not the world space, but it's normalized so that it has a single mode. rather
Yeah.
than this ambiguity of multiple modes.
Yeah, I understand. So afterward, we have to get the
You have
result.
to revert back.
Yeah, so we use something like PNP to convert between the
No,
okay.
it's an equation.
Yeah, yeah, and there will be a lot of this backend for the conversion.
No, so because it's actually a closed form solution, there's no loss. It's lossless. Like you don't sacrifice anything.
But afterward, the model assume everything is shot by a camera that has constant focal length, right? So yeah.
So we're converting cameras to a single camera. Camera here is defined by the focal length.
Yeah, but it's
Maybe we can take this offline. I think that I kind of understand your confusion.
yeah.
But maybe, yeah, we can talk after.
Okay, thank you.
Yeah.
So your treatment using the 3D uncertainty is quite interesting. Could you say more about how to estimate 3D uncertainty? Are there any typical methods or?
It's just an output of the neural net. So if you look back at the model architecture, these are all the 3D box properties, and this is uncertainty. There's a scalar that's predicted for every detection.
Do you need to use any specific architecture to measure this, or how much trust can you have on this?
How much trust can you have on this? I think that it was actually, I don't even think that we do any clipping. I think it does make training a little bit stable at the beginning, but it actually, I don't know if Garrick is Garrick here? I don't know if he's here, but yeah, Yes, Mr. Advisor.
So how are you dealing with, so you're not using categories in any specific way. So it's category agnostic and whatever you have in the data, right?
Correct.
Now, if there is a category which has a fair amount of size variation, then does that not land up introducing an ambiguity? So if you have humans, then we land up estimating their distance based on the fact that we assume they are on like 5 feet 6 inches.
Right.
Now, if you have, for example, big cars and toy cars and so forth,
Yeah, I think.
What are the consequences of that?
What are the consequences? That's a great question. We don't make any assumptions whatsoever. It is whatever the data has. So if we never see a toy car and at test time we're giving a toy car, I think the model will assume that it's not a toy car. However, it will play. It's very likely. I actually don't know if we have. I see you. Hi. Have we tried any examples where adversarial like that, where we try to fool the model? I want to, this is a great suggestion. I want to try it because I also wonder whether the contextual cues will help it.
Yeah, so that's a trade-off. See, getting some benefit from the spatial layout and other objects and so forth. And what I want to understand is if the reasoning was totally local, then you are screwed. Then it has to just estimate the wrong distance. But if the reasoning captures some spatial layout, then you have a chance to recover.
Correct. I think we should investigate that. But we haven't looked. I mean, it's a great suggestion. We should look into. Yeah.
So to follow up on the question, so you have some like a pose definitions for the objects, right? So but like
rotation, yeah.
Yeah. So for Dalek, so to define a proper pose, do you need to assume some kind of
yes. So it's not a pose. It's not a pose like a canonical pose, like this chair. The back means that it always has to be shifted right. We made this design actually on purpose because most objects don't have a definition of a canonical pose. Like a bottle doesn't have a canonical pose because it's symmetric. Pose for us means the rotation of the 3D object so that it tightly matches the object. So it's not axis aligned. It's not an axis aligned prediction. It's a rotator prediction to tightly capture the object.
So how do you handle this object? Like if you have some kind of symmetric.
Yeah. So this is where the chamfer distance comes in, and that's why it's a great loss because it makes it. You don't have a loss in the pose. You have a loss in the 3D points. So it's all about bringing the 3D points together, no matter what pose that is. This is the other benefit, but I didn't, this is extreme detail and I didn't want to confuse everyone, yeah.
So, about the virtual camera, so first, there are these losses in depth estimation that try to handle the same issue because many of the depth estimation, they're not about 3D bounding boxes, but that has the same ambiguity, right?
Correct.
You see focal length changing, you don't know how far the object is. Like there are these inverse losses that are optimization, so they're off by the actual loss by a coefficient plus a constant. So
Correct.
it seems like to be capturing some of that. And
So one of these methods is actually doing this.
okay.
It's actually.
But
and-
what is the difference? I think mathematically aren't they equivalent?
Uh,
There's a linear transformation that is.
I think that they're trying, I don't remember in this particular case, but here they also try to normalize with a focal length
Yeah,
or
they
somewhere
do
along
like
that.
they do a linear normalization per image. So there's like a shift of a constant and then projecting into a fixed state,
Yeah,
which I think if your equation is basically like focal length is a coefficient. And you don't have that offset to self. I'm not sure how they're different.
yeah, but I'll have to check the particular work, but there is a family of 3D object detector methods that are trying to be sensitive to focal length, but I think that they're missing. I don't remember exactly. I'll have to go back and
These
read
are
them.
most appear in the depth because 3D object detection is more new, but depth
Correct.
people have been-
And honestly, depth is the biggest
Right.
culprit here.
And then
predicting
is your
depth.
Z now actual metric depth? Because
Correct.
but then you're losing the focal length. How do you?
No, but we're converting back. So we're predicting in virtual space. Come on, slide, update. We're predicting in virtual space, and then we're predicting depth in virtual space, and then we invert it to get back to world space with this equation.
But do you predict the focal length?
No, we assume we know a focal length.
Oh, okay.
But even with a known focal length, because you have many focal lengths, it's still a very ambiguous problem.
Sure, but at test time, you assume the sensor. I see.
Yes. At test time, we assume focal length, yeah.